So logistic regression had a brief introduction last time, but I'll just explain again how you get from a general linear model, which could be expressed like this, so it's just a linear equation, how you get to a logistic regression from that. In logistic regression, you're actually trying to predict a probability rather than a continuous measurement that you were predicting in a general linear model. So this y is your observations, which will have a value of 0 or 1, something happens or it doesn't, so you can code them as 0 or 1. They're going to be predicted by a probability in the model plus an error term. But in terms of modelling a probability, I mean, you've got to be quite careful. You can't model it on a linear scale because it's got a range of 0 to 1. You can't have negative probabilities, you can't have probabilities of greater than 1. So that's where this transformation of probabilities comes in. So that's called a link function. And in the case of logistic regression, you take the log of this predicted probability over 1 minus the predicted probability, and you say that that's equal to the terms in your model. So we're now expressing those on a linear scale. So it's this log of the probability over 1 minus the probability which links the parameters in the model to the actual data, which is something that has a value of 0 or 1 because it may or may not happen. And this graph just sort of illustrates how this value here, which is sometimes called a logit, and it has a range, you know, it's got a linear range, it can go from minus infinity really up to plus infinity. But if you back transform that value to get the probability, it's always going to have a range of 0 to 1, which is exactly what we want to have a probability. So that's the trick that's involved in logistic regression. So you can do your modelling, but you can base the outcome on a binary variable.